Hello there, Energy 301 students. Dr. Shragi here, and we're ready to start Module 4 in ATS 564 and Energy 301. And this section of the course is going to be just a quick overview of what we're calling descriptive statistics. And we'll learn in just a little bit about what the difference between descriptive statistics are and other types of statistics that we could be talking about in this course. We will be using lots of types of statistics in this course. By descriptive statistics, we're going to be talking principally about things like averages and variance and standard deviation and quantiles and so on, and also the graphics that you would use to represent such basic statistics. With time, we're going to be learning more about ways that you could use then these statistics as part of modeling, say the electrical load or the production of power at your plant or whatever, but it'll take us a couple of modules to get to that point. Statistics, of course, is fundamentally about the uncertainty in a system. We are talking about the ways in which we can't necessarily know exactly what's going to happen or exactly what the properties of a system are. What is the mean income in the United States? That's actually a really hard thing to get to the bottom of. What is the expected amount of power that this power plant can produce? Again, surprisingly difficult to get a handle on. You need statistics. These kinds of statistics can help you evaluate or quantify or make inferences and forecasts in the face of such uncertainty. You can use these statistics to start getting a handle on what is going on when you aren't in control of everything, like how much sunlight falls on your solar panel, or how much wind is blowing through your wind turbine, or how much demand there is for power on your power grid. If it isn't obvious, the atmosphere is actually full of examples of uncertainty like this, and it's not just uncertainty in terms of what's going to happen next, but there's lots of other sources of uncertainty when we're talking about things in the atmosphere. For example, our measurements. Our measurements are never infinitely precise, and in fact, lots of measurements that we take in the atmosphere are surprisingly imprecise. They have surprisingly few significant digits. We only measure temperature to a degree, sometimes to a tenth of a degree. We only measure pressure to a tenth of a millibar. We only measure the wind speed to with an accuracy of 1 knot. And that's a nautical mile per hour. There's uncertainty then in our measurements, and there's also uncertainty in our models. How do we actually represent how we think the physical processes that are going on that are going to be able to make forecasts in the future? Our models are imperfect. There's assumptions behind there that may or may not be entirely appropriate at the present time, and so on. There's sources of uncertainty in the model itself, and of course, ultimately, there are sources of uncertainty associated with our physical understanding of how the world works. There are ways in which we just don't necessarily know very much about, how the surface of the Earth is interacting with the atmosphere. That's a big source of uncertainty in numerical weather prediction and so on. It's very difficult to determine how much of the heat from the sun will be transferred to the atmosphere by conduction, how much will be transferred to the atmosphere by evaporation of water off the surface, and so on. Very difficult problems. The basic science, the physical understanding of how the world works, can be a real challenge for atmospheric scientists, for anybody else. And so, as a consequence, statistics tends to be really fundamentally important to meteorologists. I mean, you can well imagine that we use statistics to describe the climate, we use statistics to describe probabilities that things are going to happen, and so on. But more to the point, statistics are important to lots of different disciplines. I mean, clearly we're going to need statistics for similar reasons in engineering. Economists are going to need statistics to be able to describe processes that are happening in the economy. In general, scientists are going to use statistics to describe the results of experiments. In the face of uncertainty, when they didn't know what all was going on, to be able to describe the processes at work, you're going to need statistics. And we're going to divide the statistics that we're going to be addressing in this class into two broad categories. This module is primarily associated with descriptive statistics. These are going to be things like averages, or the variance. If you're not familiar with that term, you will be. Correlation, how two data sets are related to each other. They're going to be just describing what is going on in these variables. In contrast, there's also inferential statistics. Inferential statistics is associated with like how do we make decisions based on what the statistics are telling us. That can be things like the statistical significance of the results. Are these results greater than what you would expect to happen by chance? Forecast, how do you build a statistical model that is going to be using this information to then make predictions about how much electrical load there'll be on the grid, or how much power your plant is going to be able to produce, or whatever, and also finding patterns in the data. Those are all inferential types of statistics, which will come later in the course. Right now we're going to be talking about descriptive statistics that help us organize and summarize data. These are generally the types of statistics that you are by and large most familiar with. And if you have enough data to work with, descriptive statistics can help us to comprehend and understand what is going on. We can see how the average of the amount of power produced at this wind turbine was greater than the amount of power produced at that turbine. Or we can learn that the average temperature here was greater than the average temperature there, or so on. We can use these statistics in the ways that we visualize them to understand what is going on. But statistics can do more than just tell us the general characteristics of the data. They can also tell us something about where these data come from and what they mean. This is of what we call inferential statistics. Statistical tools that let us draw conclusions about what the data are telling us. And these kinds of things tend to take more time to explain. We're going to be getting to them a little later in the course. But before we can actually get to any of this stuff, we need to spend some time on these descriptive statistics and some of the terminology that we use when we're talking about statistics and statistical sampling and statistical experiments and ultimately making statistical models, which is where we're heading in a class called Modeling Electrical Load and Yield. One possibility is just that we need to talk about anyway, a vocabulary word is numerical event. Numerical events are events of major interest to the scientist or the engineer or the business person or whatever that are identified by numbers. This is called a numerical event. So for example, a scientist might be interested in the volume of the material in his beaker, or the mass of something that he's using in his experiment. Or they might be using rulers to measure the size of these plants that they're growing as part of their experiment. Or a meteorologist might be talking about quantifications of like the speed of the wind or something like that. If we're talking about like in the world of energy, we might be talking about things like the amount of solar radiation reaching the surface of the Earth, or the amount of power produced by panels on the roof of a house, or maybe the amount of wind power being produced by a turbine, or the amount of energy being produced by a coal-fired power plant at the present time. All of these are examples of a numerical event. They're something that we can describe in a quantitative way, quantitative, as in like we can measure it, we can assign a number to it, and so on. Because the value of a numerical event depends, it'll depend on which time you're measuring it. Every time you measure, you'll get a slightly different value. Over the course of repeated samplings, a good term for a numerical event is a random variable. The process that you are examining is the random variable. We'll see examples of the usage of this terminology in a little bit. A random variable, though, a good dictionary definition of a random variable is that it is a real valued function for which the domain is the sample space. Oh my goodness, that is a difficult definition. It would help if we knew what we meant by sample space. A sample space is the set of all possible outcomes for the measurement of the observation. And we're going to be able to see this a little bit better when we see an example. But a random variable is the process that we're trying to get a handle on. What is the average temperature in Omaha? What is the average amount of power that this power plant is producing? What is the average electrical load in this neighborhood? What is the process that we're trying to study here? That is the random variable. Every time we measure it, we're getting a slightly different value because the amount of power reaching the ground from the sun is different, or the amount of power being produced by the wind turbine is different, or the load because people are turning things on and off in their house is every time they measure it is a little bit different. All the possible outcomes constitute the sample space. And our random variable is a function of that sample space. We're drawing across that sample space. The population is an important vocabulary term when we're talking about statistics. A statistical experiment involves the observation of samples selected from a larger body of existing or conceptual possibilities called the population. The population is all the possible samples that you could take. So, like, for example, if you are talking about the temperature in Nebraska right now, there is some average temperature in Nebraska right now, and there are a vast number of different places you could measure the temperature at any given time. That is the population. All of the places that you could possibly do it, that is the population. What you draw from that is the sample. The sample is a subset of the population. It is the set of observations that you actually take from the population. So, like, if you were trying to study the average electrical load in a neighborhood, you might have a sample of houses in the neighborhood. Okay, you could have chosen from a very large number of possible houses, but you selected a sample. That would be the population of all the houses. Either literally all the houses that really are there, or even conceptually all the houses they could build there. And then you selected a sample of those. Possibly it's best to think about this in terms of an example. Let's say that you were interested in studying the amount of power that was being produced by some wind turbine. This is the random variable then. Amount of power to be produced by this wind turbine. And let's just give that this is our numerical event, that is instantaneously how much power is this wind turbine producing, and we'll call that random variable right now P, okay? And we're going to have an infinite number of possible times we could test that and get an observation of what the instantaneous flux of power, or instantaneous amount of power being produced by that wind turbine could be. I could do it now, I could do it then, I could do it 10 minutes ago, I could do it 10 minutes from now, I could do it averaged over a 10-minute period, I could do it averaged over a day, I could do the power next week. There's an infinite number, there's a population of just an unlimited number of times I could do this. The sample is going to just be, from that population, we're going to be taking then a sample of just okay, here are the 10 times I'm going to measure it. I'm going to measure the wind power coming from this wind turbine every day at noon. Okay, that's my sample for 10 days. That is our sample. And we would have then a number associated with that, and we would number our samples from 1 to n. So we have value P1, that's the first time we measure the power off our windmill. P2, the measure of the power measured off our windmill the second time, all the way up to Pn, the nth time that we have measured power coming off of the turbine. So out of all the population of all the possible times we could have taken the measurement of how much power the wind turbine was producing, we in fact did sample it n times. Okay? Now, there are huge issues right there. There are whole courses out there about how you decide when to sample things. There can be biases. For example, let's say I took my sample of my 10 times I was measuring the amount of power off my windmill, but I took them all in the late afternoon. Well, a meteorologist can tell you late afternoons tend to be windier than, say, overnight. The amount of power that you are thinking that this windmill is producing by measuring it late in the afternoon doesn't reflect very well the average power that the windmill is producing, because you're forgetting about the fact that at night there is less wind power. In general, nights are less windy. There are huge problems with sampling. That's a whole course. We're not going to get really bogged down into that, but we're going to be starting to think about instead, how can we describe the sample? What are the statistics that we can compute? And by statistic, I'm putting that word in quotation mark here. This is going to be a defined term. Statistics. They're going to be numbers like the average. And that's going to be in contrast to kind of the opposite of a statistic, if you will. I'm not sure opposite's the right word, but in contrast to a statistic, there are parameters. And the parameters are what we're actually trying to get a handle on. They are the actual, but unfortunately usually unknowable, properties of a real population, not the sample. An example of a parameter is the mean. Now, this is getting a little tricky to think about, and so what we probably need, rather than get all confused, is if we're going to talk about the difference between statistics and parameters, and how parameters are usually unknowable, and how we are, let's go ahead and talk about parameters and statistics for a moment. Let's say that you had a problem. You've been somehow tasked with the job of finding the mean temperature in Omaha right now. Okay, what are you going to do for that? Well, you could take the temperature at the official National Weather Service location for Omaha, which happens to be Epley Airfield. Okay, But see, here's the deal. That temperature is not, in general, going to be the same as the temperature measured at the National Weather Service office, which happens to be out in Valley, Nebraska, about 20 miles west of Creighton. And in general, that's not going to be the same number. And, you know, I could sample the temperature at another location, like maybe down at there's an official Weather Service weather observing station out at Offutt Air Force Base. Okay? But, again, that's, in general, not going to be the same number. Well, what about the temperature at, there's an official observing station at the Millard Airport. Okay, well, we could take that as well. And, again, in general, it's not going to be the same. And, for that matter, there's any number of elementary schools that have well-calibrated thermometers and television stations and radio stations. There's a large number of places we could do this, not to mention just any backyard or any street corner or any parking lot. What are we going to do? There's a large population of places we could be measuring the temperature. No matter how big our sample is, no matter how many places we have measured the temperature, we haven't measured it everywhere. No matter what we're getting is a result that depends on the sample that we took. I mean, there really does exist something that is the mean temperature right now. Mean temperature is a parameter. It is really describing physically what's going on. There really is a mean temperature over Omaha right now. It is a parameter. The problem is there's no way to know it. There is no way to actually know what that mean is. Rather, the best we can hope for is to take a well-designed sample and then, based on that sample, compute the average. You know, add them up and divide by n kind of average. Okay? That's a statistic. A statistic is just a number that we compute based on the sample that we took. It is a way, as we'll see, of estimating the parameter, but it isn't the parameter. Taking the average of these 4 weather service stations that I've got here on the plot is not the same thing as actually taking finding the mean, but it's kind of in some ways the best we can do. And so, in general, there is no way to know the parameter. And there's lots of parameters that we want to know. Things like how two variables are related, or how the distribution of data, like as in what its histogram would be over a large sample, or other properties, the most common observation, or something like that. Although the one that we talk about most of the time is going to be mean. Okay, the kind, you know, the mean of the data. That's a parameter. But in general, it's not possible to know them. But you can estimate the value of the parameter with well-chosen statistics. Average is an estimator of the mean. We'll have other estimators of the mean in a future lecture here. It should be pointed out, though, shockingly, the statistic itself, like average, is itself a random variable. I mean, if I took another sample of 4 places around Omaha to measure the temperature right now, I'd get a different average temperature for Omaha. And if I measured it 4 places again, I'd get a different one. So the statistic itself, like average, has properties to it, like how it has a mean, like over a large period of time, the more places I took the temperature, the closer I'd be getting to the mean. It has a range that we would expect. It has quartiles and quantiles and all that kind of stuff that when we could talk about like what is the highest average temperature and the lowest average temperature and so on. Statistics themselves are random variables. Oh my goodness, that is hard to wrap your head around. In this module, we're going to just be focusing on descriptive statistics, understanding and learning how to compute and visualize descriptive statistics. How are we going to be using our tools to understand what does the average actually tell us? What does standard deviation actually tell us? What does the correlation coefficient tell us, etc. So that we can start then using those tools in future modules to start making models, like statistical models of power or electrical load or whatever. So that's where we're going with this, and all this vocabulary and terminology that we had in this first lecture will really help you as we move forward here. Now, before we move forward, I do want to ask you a couple questions about what we just learned here. Now, all 3 of the questions here have the same setup here. Suppose I'm trying to determine something about the electrical load for a city. The city is at some given latitude and longitude, it has some number of residences, and it has a certain fraction of homes with smart energy meters. In a problem like that, what's the random variable? A, the electrical load, B, the location of the city, C, the number of residences, or D, the fraction of homes with smart energy meters. Okay, that's kind of a tricky question. Take a stab at it, answer it with one of the links below this video, and we'll see how you go how that goes for you before we move on to question 2.